All right, last key for this homework week. So for this last one, we're now dealing with conservation of energy, no longer just um, kinetic energy and work. So in this case, we'll be looking at gravitational potential energy as well as spring or elastic potential energy. So the first two questions are easier to explain in words than they are to really show in writing. So the audio of this might be more helpful, but if the height of a playground slide is kept constant, will the length or the presence of bumps make any difference in the final speed? And the short answer is no, it doesn't matter. And the reason for that is that no matter what the slide actually looks like, if the slide is very steep, or if the slide is shallower, or if the slide has all kinds of little bumps. That's a great slide drawing. For all of them, if you think about the energy transformations, energy initial has to be equal to energy final. And all of that energy initial is gravitational potential energy. And all of that final energy is kinetic energy. Well, what makes up that gravitational energy? It's mass times g times h. And the kinetic energy is 1/2 mass times v squared. And if you look at this, it's obvious that mass cancels. And so the defining factors for velocity is going to be the square root of 2gh. In other words, the velocity depends only on gravity, which is the same for all of the slides, and the height of the slide, which is the same for all of the slides. So assuming a frictionless surface, there is no difference in the speed of a slide at the bottom as long as the slide has the same overall height. So that's the answer to the first part of this question. For the second part, here, maybe I'll try doing it this way. I'll try highlighting that in purple, and then I'll highlight this in purple so that you can see that they're associated with each other. And then for this part, this will be my sort of peach, I guess, is that. So for the second part of this, if there is friction, work is force times displacement, right? And let's assume that the frictional force is approximately the same for all the slides. And that's, assuming that they're made of the same material, then the slides would have the same coefficient of friction. In that case, once the coefficient of friction is the same, then the force of friction is going to be based on that normal force. And as you can see, when you have a very steep slide, Fn is small, right? Because the angle is so extreme. And when you have a slide that's medium, the normal force is medium. And when you have something like this last one, the normal force will be at its largest at these highest points of the slide. So here, the normal force is large. Similarly, displacement is going to be small for this slide. It's the shortest overall slide. And displacement for this slide is going to be medium. And displacement for this slide is actually going to be pretty large. Like there's a much more significant amount of slide there to cover. So in this case, there's going to be lots of negative work for longer slides. Negative work means negative change in kinetic energy. So longer equals slower. In other words, when there is friction, the length of the slide and bumps matter. When there's no friction, they don't matter. Color code that too. Oh, that's not right. Cool. So for this next one, we've been saying a lot that work is equal to delta KE. Work equals delta K. That's really the true work energy theorem, but I have been sort of cutting corners and saying that work is actually equal to just change in energy as a whole, because there are examples where you can create a scenario where it appears that kinetic energy is not changing, even though energy is changing. And the easiest example of this would be an object that moves up a force of a lift that is equal to the force of gravity, so that this object is moving up with constant velocity. So it does have a displacement in the upward direction, because if it's moving at constant velocity, that means that kinetic energy is also constant. But if it's moving up in the air, that means that GPE, gravitational energy, is increasing. And why is it increasing? Because you're exerting a force over a displacement. So in this case, that means positive work, even though the kinetic energy is not changing. So that's the easiest example of this. So now getting into some actual calculation problems, we had 1A here. Let's call, and for A it says we're going to call 0 the position at point B. So we have a roller coaster on top of a rise. It moves 135 feet at an angle of 40 degrees below the horizontal. So basically, it's an inclined plane. Oh my gosh. Where this angle here is 40 degrees. And my coaster is moving down this at 135 feet. So first off, I know my mass is 1,000 kilograms. I know G is 10 meters per second squared. And remember, because energy can't be negative, it's a scalar quantity. When we're doing energy problems, we do not assign a negative sign to G. G is always positive in an energy-related problem. And then lastly, I am looking for the gravitational energy at point A and B, and the change as it moves from one to the other. So I'm looking for UG at A, UG at B, and change in UG from A to B. So UG, or gravitational potential energy, is mass times G times height. And in this case, I already know mass and G, so this question is just saying, what are the heights at these 3 points? Then plug those heights into your equation. So the first thing we need to do in order to solve this problem is to convert 135 feet to meters. And that comes out to be 41.15 meters. So delta X is 41.15 meters. Now, that is not the change in height, right? This is my change in height, delta H, and that's going to be 41.15 times sine of 40 degrees, which is equal to 41.15 sine of 40, 26.45 meters. So for the first part of this question, UG at A, that's MGH at A, which is 1,000 times 10 times 26.45. So the gravitational potential energy at point A is going to be 264,500, 264,500 joules. At point B, well, we defined that as height 0. So at point B, if that's height 0, then the gravitational potential energy at B is also going to be 0 joules because you're multiplying by a height of 0. And then lastly, delta UG, the change in gravitational potential energy, that would be UG final, or at B, minus UG initial at A. So that change in gravitational potential energy is going to be negative 264,500 joules. Did not manage my space very well there, but we did it. We got it all done. For question number 2, we have a child on a swing attached to a rope 2 meters long. So let's diagram this too. We have a swing where the length of this rope is 2 meters. And it also says that we're going to define this lowest point as height equals 0. So part A, when the rope is horizontal. What is the gravitational potential energy? In this case, what we are given is 400 newtons. Now, hopefully you are noticing that 400 newtons, that is not the mass of the child, that's the weight of the child. That's saying the child's mass times gravity is weight. Weight is mg. So this 400 newtons actually includes both m and g. So my gravitational potential energy, all I have to do is multiply the 400 newtons, m and g, by whatever the height is. When the rope is horizontal, then my height is 2 meters. So UG is 400 times 2, or 800 joules. Easy. For part B, the rope has a 30-degree angle from the vertical. So now in this case, I need to find what that height is there. So I have a 2 meter long rope. That's the hypotenuse of my triangle here. The height of that, the vertical component of this triangle here, is 2 cosine 30, which is 1.73. So this length here is 1.73 meters. That is not the height. The height is this remaining piece. The second height is going to be the 2 meters minus that 1.73. So the actual height here is 0.27 meters. So in this case, I'm doing UG equals mgh. That's 400 newtons times 0.27 meters. 107.18 joules. So that's that one. Last two. So here we have a high jumper. And this is where energy problems start getting fun, because in this case, we're given a velocity and we're asked about height, right? How far does his center of mass move up as he makes the jump? So really this question is asking me, what is the height? This question incorporates the principle of conservation of energy, saying the energy at the beginning is equal to the energy at the end. When the jumper leaves the ground, all of the energy that the jumper has is in the form of kinetic energy. And when the jumper is at its highest point, all of the energy is in the form of gravitational energy. And so this is the simplest way to solve this problem. Now, yes, you could do this as a free fall problem, just giving the initial velocity of 6 and the final velocity at the highest point of 0. You could solve this using kinematics as a free fall problem, but it's actually easier to use energy in this case, because what we get is 1/2 mv naught squared equals mgh. Mass cancels in this case, and I'm solving for h. So what I get is h equals v naught squared over 2g. To simplify that, that's super easy to do because I know v naught equals 6 meters per second and I know g is 10. So 36 divided by 20, which is a height of 1.8 meters. So you can see how much simpler using energy makes this problem. Lastly, we finally get a little spring energy in our life. And again, this problem is going to be utilizing the principle of conservation so that the energy at the beginning is equal to the energy at the end. For part A of this problem, the energy at the beginning is actually all in the form of spring potential energy because you have a compressed spring. At the end of this first part of the problem, the energy is all in the form of kinetic energy. The reason I know that is, for one, as a spring pushes on the object will speed up. And I also know that the spring is momentarily exerting no force. And what that means is that the spring must be at its equilibrium position, right? That's where it's relaxed spring. So for this problem, I know mass is 0.15 kilograms. I know the K value of the spring is 10 newtons per meter. And I know the displacement of the spring is 0.18 meters. You could call that negative 0.18 meters. It doesn't really matter because in my problem, I'm going to be squaring that number anyway. So plugging this in, my formula for spring energy is 1/2 kx squared. And that's going to be equal to the kinetic energy 1/2 mv squared. Plugging in, I get 1/2 times 10 times 0.18 squared equals 1/2 times 0.15 v squared. And solving for v, I get an answer of 1.47 meters per second. Hopefully I plugged that into my calculator correctly. So that's part A, right? Again, conservation of energy. Now, you could also solve this using Newton's laws and forces. You would use the integral of the force of the spring to find its change in velocity using Newton's second law. That's a lot more work than just applying energy in the first place. Last part of this question is when it's 2.5 meters from its starting point. Now that 2.5 meters is a little bit tricky because that number gives me some information. That means that my position of the spring relative to its resting length is going to be 0.25 meters minus the 0.18 meters. And the reason for that is that 0.18 meters was its initial displacement in one direction, right? So that was like a starting displacement of negative 0.18 meters. Now its new position is 0.25 meters in the positive direction from that. So negative 0.18 plus the 2.5, that gives me an x of 0.07 meters for this second part of the problem. So my new x is 0.07 meters. And in this case, what that means is that my energy at the beginning is still going to be equal to the energy at the end, but my energy at the beginning is spring energy, and my energy at the end is going to be a combination of spring energy and kinetic energy. It will both be stretching a spring and still be moving. So plugging in my energy formulas, I get the 1/2 kx squared, that's x naught, equals 1/2 kx final squared plus 1/2 mv squared. Again, that's 1/2 times 10 times 0.18 squared equals 1/2 times 10 times 0.07 squared plus 1/2 m v squared. I'm sorry, where the mass is 0.15. So again, all long problem, but only one unknown variable. So you can plug this into your calculator and you can solve for V. And hopefully I plug this into my calculator right. I get a velocity here of 1.35 meters per second. That answer should make a little bit of sense to me because we're just slightly past the point at which it's at its 1.47 meters per second. Just going slightly past that point, I would expect the velocity to be slightly smaller than it previously was. So that all sounds good. Hopefully you've enjoyed this. Last time I gave you a picture of a turtle. This time I'll give you a picture of a butterfly. And put some pretty colors on it. How about violet? Yay! Enjoy.